Okay, question 3, which is 2 questions on proof by induction. You'll notice there should have been a Z here as a typo or misprint. So positive integers, positive integers. So the first one we're showing that that recurrence relation works for any value of n greater than or equal to 1. We find the first few terms. So to get the next term, we do 4 times the previous term, take away 9 times the number of the previous term. So it doesn't ask us to do this. So for example, u1 is 8. u2 is 4 times 8, take away 9 times 1. Because remember, this is n plus 1. This is n. So n is 1, so u1, 9 times 1. Okay, which is 23. u3 would be 4 times 23, take away 9 times 2. 4 times 23 is 80, 92. Take away 18 is 74. And so on. Now we're asked to prove that un can be written in the form 4 to the n plus 3n plus 1. Okay, so for example, so we test. So let n equals 1, because we're trying to prove it works for n is greater than or equal to 1. Then we've got u1 equals 4 to the power 1 plus 3 times 1 plus 1, which equals 8. Okay, to check our understanding, we could put n is 2 and we get 23 and so on. But we're not going to do that. We're going to prove it works for all by induction. So therefore, we can say it's true for n equals 1. Okay. Now we've got to assume that it's true, or there exists a k such that this works. In fact, we know it works for 1, but we're assuming a general k such that uk is 4 to the power k plus 3k plus 1. And what we're now going to do is prove that if it's true for k, then it'll be true for k plus 1. Okay, and because we've shown it's true for 1, it'll be true for 2. If it's true for 2, it'll be true for 3, and so on. That's the general principle. So we've got that. Now we know that uk plus 1 is from the connection right at the top. Okay, is 4 uk take away 9k. Right? So that's equals 4 uk take away 9 lots of k. Now we know what uk is, we've written it down, so we've got 4 lots of 4 to the k plus 1 plus 9k. Right, if we expand that out, we get 4 to the k plus 1 plus 12k plus 4 plus, oh sorry, it's minus 9k, which equals 4 to the k plus 1 plus 3k plus 4 is 4k plus 1 plus 3 lots of k plus 1 plus an extra 1. Okay, so we've got it in the same format as this one up here, but all the k's have been replaced by k plus 1. Okay, so replace that with a k plus 1, that with a k plus 1, and we've got this expression. So therefore, it's true for n equals k plus 1. And now we just have to put our final statement. Okay, since it is true for n equals 1, this implies it's true for let's do for all, let's do a mathematical symbol, for all n greater than or equal to 1. Okay, so we've shown it's true for 1, we've shown it's true for k, therefore it's true for k plus 1, Therefore, since it's true for n equals 1, it implies it's true for all n greater than or equal to 1. Okay, now part B is a very similar process. Bottom of the page. So we're trying to prove that 3 minus 4, 1 minus 1, the power m equals this expression here, 2m plus 1 minus 4m, m, 1 minus 2m. Okay, now we obviously so we let m equals 1, then we get 3 minus 4, 1 minus 1 equals, put 1 in, 2 times 1 add 1, 1 and so on. We get 3 minus 4, 1 minus 1. Therefore, true for m equals 1. Okay, so we established it works for 1. Now we're going to move on. We're going to say, well, assume there exists k, so it works for some value k, the general value, minus 4, 1, minus 1 to the power k equals this, oh, not m, k, sorry, 1 minus 4k, k minus 2k. Now we're going to show then, if that's true, then we're going to say, well, 3 minus 4, 1 minus 1, so k plus 1, clearly equals 3 minus 4, 1 minus 1, power k, times an extra bracket. Okay, when we multiply those out, okay, we're going to replace that with that. We want this same expression, but with all the k's replaced by k plus 1. So k plus 1 here, 2 lots of k plus 1 plus 1 here, and so on. Alright, so we've already assumed that power k equals this. So we've got 2 to the k plus 1 minus 4k, k, 1 minus 2k, 3 minus 4, 1 minus 1. Okay, now we're going to multiply those two together. So cross and down, so we get 6k plus 3, which is that times that. That take away 4k is the first term. Cross and down, and we get minus 8k minus 4 plus 4k. And bottom left, we get 3k plus 1 minus 2k. And bottom right, we get minus 4k minus 1 plus 2k. Almost done. So this equals, remember what we're looking for. So we've got 2k, I'll do it in 2 steps. You possibly could jump, but we'll do it in 2 steps. So here I've got 2k plus 3. I've got minus 4k minus 4. Down here I've got k plus 1, which is encouraging. And here I've got minus 2k minus 1. Okay, so finally I just need to put it in the right format. So now I can write this equals 2k plus 1 plus 1, comma, minus 4 lots of k plus 1, k plus 1, and 1 minus 2, k plus 1. Okay, so I've just got that is in the same format as this one up here, just all the k's have been replaced with a k plus 1. So that's the same. So therefore we can conclude, therefore true for m equals k plus 1. So therefore, since it is true m equals 1, that implies it's true for all m greater than equal to 1.